All right, so here we are in section 16.2. We're talking about line integrals. Line integrals are one of the primary topics of focus in chapter 16, and they're one of three new integrals that we're going to define in this chapter. Line integrals, and then later on we'll talk about surface integrals and volume integrals. So to motivate this idea, I want to think about what an integral really is. When you first learn about integrals at the end of Calculus 1, you talk about how a definite integral represents an area under a curve. In particular, an area between a curve and the x-axis over some interval AB. In chapter 15, we expanded on that idea with double and triple integrals. In particular, the double integral idea, we started by thinking of it as a volume under a surface over some region in the xy plane. We started by thinking of those regions as being rectangular, but then we talked about more general regions like type 1 and type 2 regions. And there was that interpretation of volume there. Now, my opinion is that the interpretation of single variable or integrals of single variable functions as areas or as two variable functions as volumes, it's a useful way of thinking about what an integral is when you're first learning it, but it's not a good way to think about integrals in general. There's a lot of different types of integrals out there, even beyond this class, over lots of different types of functions, and the majority of them you actually can't really interpret in terms of area or volume. Really, the central theme in integration is that of a Riemann sum. So what is a Riemann sum? Well, informally, the ingredients that you need for a Riemann sum are a function, the thing that you're integrating, and a subset of the domain of that function that you can break into pieces. So if you think about a function of one variable that's got, contained in its domain the closed interval AB, you can integrate that function over that closed interval AB under certain conditions. And the way that we define that that integral in terms of a Riemann sum is we take the interval AB, break it up into subintervals, choose sample points in those subintervals, and then use those sample points in our function to approximate that integral, and then applying a limit to the sum the sum of those things that we create is what gives us an accurate answer. So it takes our approximation into an exact answer. That interpretation has applications all over the place. In Calculus 2, anytime we introduce a new application for an integral, whether it's center of mass or hydrostatic pressure or even volumes of revolution, things like that, we always start by thinking of an approximation of what we're looking for in terms of a Riemann sum, and then applying a limit to that, which is where the integral comes from. But most of those applications don't have anything to do with area. So it's the Riemann sum idea that matters when we talk about integrals. And with that, I'm going to kind of launch into this discussion of line integrals. So let's talk about the environment that we're in first. For now, until a little bit later in this section, we're going to be dealing with functions of two variables, f of x, y. Now, let's take a look at this picture for a second. We'll go into more detail on this in a moment. But when we've done double integrals back in chapter 15, the subsets of the domain of f of x, y that we were integrating over looked like regions that have area. So you can think of them as like a two-dimensional part of the domain that we integrate over. Line integrals look to the domain of f of x, y as well, but instead of integrating over some two-dimensional region, we're integrating over a one-dimensional curve. This curve, we're going to assume, is still contained in the domain of our function f of x, y, but it's no longer a region, it's a curve. So how can we make this idea a little bit more exact and formal? Let's just say that we have this curve C, and it's in the plane, the xy plane, and it's also in the domain of the function f of x, y that we want to ultimately integrate over. I'm going to say that this curve can be parametrized this way. So we're going to be dealing with a lot of parametric equations, parametric forms for curves in this entire chapter. It's important to be comfortable working in that environment. Remember, anytime we're talking about a parametric form for a curve, you can write in vector form like this. So r of t equals x of ti plus y of tj. And in particular, the curves that we deal with here have a start and an end. They have an initial point and a terminal point. So that means our parametrization has to be defined on an interval for t, from a to b in this case. We're also going to assume that c is smooth. We defined what it means for a curve to be smooth back in chapter 13. So just as a reminder, it means that r prime is continuous and non-zero on the interval that our parametrization is defined on. So what we do here is we take our parametric, our interval for our parameter AB, and we divide it up into n subintervals of equal length. This picture down here is kind of showing this. So separate from the curve in the plane, we're looking at this interval on the real line AB, and this is what we call our parameter interval. It's the interval that the t's live in. We're cutting that up into n subintervals of equal width. Now each of these subintervals will determine a subarc on this curve. Because remember, these t's are what give us the points along this curve. So little subintervals here correspond to little subarcs up here. Now, if I were to go through to each one of these little subintervals and choose a sample point, say ti star, then plugging ti star into our parametrization is going to lead us to one of the points in the ith subinterval in this case, which I'm going to call pi star. We need those sample points in order to come up with a Riemann sum. Now, in addition to that, we need to consider the length of each of these subarcs. If you think about a Riemann sum for a single variable function, we take the sum of terms that look like f of xi star, where xi star is the sample point that we chose, and then we multiply that by delta x, which is the width of the subinterval that our sample point came from. Well, in this case, the subarcs are not part of an interval, but they do have a length. And just because the parameter interval was broken up into subintervals of equal length does not mean that these subarcs have equal length. That's not a consequence of that. So each of these may have their own length, and we're just going to denote those lengths by delta S1, delta S2, delta S whatever until we have a length for each one of these. If I were to form this sum right here, the sum of all f of xi star, yi star, remember these are the coordinates of this point pi star, and then multiply that by the length of the subarc that it came from, what we have is something that takes the form of a Riemann sum. If I apply a limit as n goes to infinity, this becomes an integral. And that's what we call our line integral, which is defined here. So again, following that derivation, the notation that we use, notice there's an integral symbol, and we just use the capital C down here. This is the C that we're using as a label for our curve. The line integral of f of xy along C, and then here's this ds right here. Remember, the ds came from this delta si right here. So that ds is a differential, and it's a differential for arc length. This is important. We do a lot with this idea of the differential with respect to arc length. In fact, we'll do a little bit right after this definition. But this integral comes from the limit as n goes to infinity of that Riemann sum that we just talked about. Now, as you know from all the work that you've done with integrals, single variable, two variable, three variable, whatever, you don't stick with the Riemann sum idea when it comes to evaluating the integral. It gives meaning and interpretation to those integrals, but it's not a good way to evaluate them. It's very cumbersome to work with that definition for evaluating an integral. So we want to come up with some easier way to work out integrals mechanically. So we're going to work with this, but I want to start by thinking about the differential ds. So remember, our function up here, or our parametrization of our curve is given as a function of t, where t is our parameter here. It's going to be easier to integrate this function with respect to t than it is to s, which means I need to change the form of this. And I do that by looking at the relationship between s and t. So if s of t represents the arc length function, which we've talked about before, and you talk about in Calculus 2 as well. If it represents the arc length function for c, then based on the work that you've done in Calc 2, and we revisited that early on in this course, we know that ds dt is equal to the square root of dx dt squared plus dy dt squared. This is a previous result. We're not going to go through and derive this again. Now, if you think of ds dt as a fraction, and you were to multiply both sides by t dt, you get this. ds is equal to the square root of dx dt squared plus dy dt squared dt. And you may not be comfortable with the idea of thinking of this as a fraction, but this is justified if you think of these in terms of differentials, the way that we define differentials earlier on. We're not going to go through all that derivation, but this is what you need to remember. ds dt is equal to this. That allows me to change my ds dt into a dt. I'm going to go to the next page in a second and show you what that looks like. But really quickly, I did mention before that this, right? Maybe I didn't mention this. I can't remember now. That the line integral can, in fact, represent an area of sorts, but it's better to not really think of it in these terms. However, let's suppose that the function f of xy, that we're considering that function f of xy, and we're integrating over this curve c in the xy plane. The function f of xy is going to be in space somewhere, so that's going to determine the space curve. If I were to think of this space curve as sort of dropping a curtain of sorts onto this curve c, then the line integral would technically represent the area of one side of that curtain. It's a way of connecting that idea to the area concept.